Hello, everyone. I hope you had an interesting summit so far, and thanks for joining me for my talk on prototypical networks for interpretable diagnosis prediction. My name is Betty van Aken, and I'm part of the Datexis research group at the Berlin University of Applied Sciences. So my research group is called Datexis, and we're doing research on natural language processing with a focus on deep learning and transfer learning in particular. Today's talk will also feature two important research directions of our group, which are explainability and clinical NLP. For clinical NLP, we are happy to have an ongoing collaboration with the Charité Berlin, which is one of the largest university clinics in Berlin. And my talk today will cover two things. First, I will introduce the task of clinical outcome prediction from admission notes. And second, I will describe the method we developed to enable interpretable diagnosis prediction using prototypical networks. So what do we mean by clinical outcome prediction? Together with the doctors from Charité, we have identified possible use cases for NLP in clinical practice. And one starting point that we identified is a patient getting newly admitted to the hospital. Information about this patient is usually stored in a clinical note in a semi-structured form. And the doctor uses this information to make predictions about the patient's trajectory and to take first decisions about diagnostics or about treatments. The problem is that the time for this initial evaluation is short and that doctors might miss certain risk factors. That's why we want to support these doctors in their decision process by increasing the considered medical options and by pointing towards possibly overseen risks. We framed this as an admission to discharge task, where the admission note is the input and the state of the patient at discharge is the model output. So we have identified 4 discharge objectives here, which are diagnosis, procedures, in-hospital mortality, and length of stay. And the goal is that the model identifies multiple risk factors within the text to make predictions about the patient at discharge. As data for our task, we use publicly available clinical notes from the MIMIC3 database, which includes over 50,000 admission notes annotated with discharge information about mortality, length of stay, diagnosis, and procedures performed. But since MIMIC3 does not contain admission notes per se, we use the discharge summaries in the dataset and filter out all the information that is unknown at the time of admission. The simulated admission notes then become the input to our model. In earlier work, we have shown that an additional pre-training objective, which we called clinical outcome representations, or CORE in short, improves existing biomedical language models, such as BioBird, on all 4 outcome tasks. We have also developed a demo application for that that can be used to better understand the model capabilities and the use case. So giving it an admission note, the application outputs predictions on clinical outcomes, such as these diagnoses. And if you're interested in this work, I would like to point you to our EACL paper, Clinical Outcome Prediction from Admission Notes using Self-Supervised Knowledge Integration. And you can also find all the resources such as Hugging Face models and the mentioned demo application at core.app.datexis.com. So let's move on to the new method I want to present to you today, prototypical networks for interpretable outcome prediction. First of all, for this method, we are going to focus on the outcome task of diagnosis prediction, since this is the kind of like the most essential part of outcome prediction, because the other outcomes also depend on the diagnosis that the patient is diagnosed with. So when we used our demo and discussed the results with doctors, we found that simply listing possible diagnosis is not really enough to support in clinical decision making. So what is needed to help the doctors really in their process? We found that one thing are indicators of which patient information was important for a diagnosis prediction. And the second one is that we needed pointers to similar patients from past encounters. Their doctors could compare their clinical progression and also decisions that were made by other clinicians based on these patients. So this really is needed to not only get like a decision of a model, but to help in treating the patient in a better way. So how can we get there? When looking for possible solutions, we were actually inspired by a publication by Chen et al., which is named "This Looks Like That: Deep Learning for Interpretable Image Recognition." And here the goal is to classify types of birds, and the model bases its decisions on parts that are of the image that are identified as being very similar to prototypical parts of bird species. So for example, you can see that one part could be the beak or the feathers of a bird, and the model simply compares these parts to prototypical parts it has seen during training. And then the decision of whether a bird belongs to one species is made on this comparison. So one benefit of this approach is that model decisions can be faithfully explained by looking at these prototypical characteristics. And this is something we really liked about it. So following this idea, we were curious if we could apply the same concept to our clinical nodes. So instead of parts of images, we are now looking at parts of text that are similar to characteristics in prototypical patients from former encounters. So how can we get there? How can we set this up? To achieve this, we use the concept of prototypical networks introduced by Snell et al. And the idea is rather simple. So we have our clinical node here, and we encode it with a PubMed bird, so a large language model pre-trained on biomedical text. And then we compare the encoding, which you can see in blue here, to prototypical vectors that are learned for each diagnosis during training. So in this case, we can see that our encoding is pretty similar to the prototypical vector for cerebral hemorrhage or bone bruise. It is not very close to the spinal cord injury prototypical vector. So our classification will result in these two diagnoses instead of this one. However, this approach yielded some problems. First, because we are dealing with a multi-label setup, the encoded text needs to be close to multiple prototype vectors at once. And we found, because in the MIMIC3 data set, we have an average 11 diagnoses per patient, that this led to kind of blurry encodings and no clear clusterings in vector space, because this encoding has to lie in between many different prototypical vectors. And secondly, we still don't know which part of the text was responsible for which diagnosis prediction. So this didn't really fulfill our requirements. So to solve these problems, we introduced an additional layer of label-wise attention vectors, which you can see here. And what these vectors are doing is putting weight on each token based on its importance for a certain diagnosis decision. So you can see that for some diagnoses, tokens, for example, the light green tokens, are more important than to others. And some parts of the text might only be relevant to decide upon one specific diagnosis. So these attention vectors are then putting weight on tokens per diagnosis. And in this way, we get an individual patient representation per diagnosis that makes it easier for the model to decide whether a patient looks similar to a prototypical one. And this also helps us because now the model doesn't have to kind of decide between prototypes, but we can really fulfill the multi-label objective to have a different decision for each diagnosis here. What we have found is that reducing the dimensions of the representations to only 256 saves first memory, but also yields better results because the model is forced to focus on the most important signals here. And a second thing that we found is that the initialization of the prototype vectors actually play an important role in how fast our training converges. So we decided to initialize these prototypical vectors as the centroid of all training samples for a certain diagnosis. This has also been shown beneficial in some few-shot scenarios in earlier papers using prototypical networks. Another thing that we found about the initialization is that it is even more important for the attention vectors. So we developed a method to initialize these attention vectors based on TF-IDF and used it to build like an average of weighted tokens from all training diagnoses. And this way, we get a better starting point for training these attention vectors, which you will later see in the results is actually playing an important role. So you can see the full pipeline of our approach in this visualization. And we train our method end-to-end with binary cross-entropy loss. So both the attention vectors and the prototypical vectors are learned during training. And this approach gives us the possibility to actually retrieve the most prototypical patients and to highlight the parts of the text that are relevant for each diagnosis decision. So this way we can fulfill the requirements identified with the doctors and can now look at parts of our clinical note like this and get relevant prototypical parts back. So we increased the information that we can give out to our doctors by a large extent. And this way can actually enable better decision-making in the clinical practice. But let's look at some results. So here we look at the results of our model in purple and red compared to baseline approaches using PubMed-BERT. On the y-axis, you can see the AUROC score, and on the x-axis, you see the frequency of diagnosis in our training set. So like most tasks that we can see, we have a power law distribution. So most of our diagnoses are very infrequent in our training set, and there are some that are very frequent. And what we can see here is that the largest gains from our approach are actually made on the rare diagnosis codes that occur less than 100 times in the training set. And we also see that our initialization of the attention vectors using TF-IDF, which is the purple line here, improves in like the very few shot cases a lot. The cases that have less than 5 examples in training data. And this shows us that these attention vectors really benefit from having a good initialization if there are not enough training examples to properly train them on. What we can also see is that our approaches are more stable for different seeds than the earlier approaches. So what does that mean for the actual use case? We again built a demo application to show to doctors and also to show to the interested audience. So please feel free to go to protopatient.demo.texas.com to try it out. And as you can see, we again have an admission node as an input, and as an output, we get a list of predicted diagnosis by the models. But now we also have additional info about which part of the text the model considered important for this diagnosis. So for cardiac dysrhythmia, this might be other tokens than for the hemorrhage that we have seen before. So now we can directly see and also control the model to get an idea like what was important. So we can earlier identify possible biases as well. For example, tokens that actually should not play an important role. But we can also focus the attention of doctors to the very relevant parts in the clinical note. And in addition to that, we can now also point to prototypical patients and let the doctor scroll through these earlier encounters to see whether they can help in the current decision making. So again, feel free to try out our demo. I'm looking forward to feedback on that. And now to the next steps that we are planning to achieve with this framework, basically. So first of all, we are really very interested in how multiple prototypes for diagnosis can play an important role for this method, because right now we only look at one prototypical patient representation, but there are a lot of diagnoses that have a lot of different presentations in patients. So this could be an important improvement. And the second thing is that I would like to find out how to use the modularity of prototypical networks. For example, in using this to get feedback from doctors that could create new prototypes based on patients that the doctors consider important and prototypical. So I'm really looking forward to see how we can get feedback into the model by just introducing new prototypes. That could also be constructed of prototypical cases from literature or from medical experience, like from day-to-day practice. All right, if you're interested in the details of my work and in what our group is doing, I would like to point you to the publication describing all of this work, which is called "This Patient Looks Like That Patient, Prototypical Networks for Interpretable Diagnosis Prediction from Clinical Text," and was published at last year's AACL. For now, I would like to thank you for your attention, and I'm very happy to answer questions after this talk or also later via email. Thank you.